This video is about vector equations of lines and how we can also find the intersection of two planes using vector equations of lines. So first, writing the equation in point-slope form of the line that crosses through 2, 1 and 5, 2 isn't that hard. First, we find the slope of that line, and then we write it in point-slope form. Y minus y1 equals m times x minus x1. You can choose either the point 5, 2 or the point 2, 1 when you write the equation. So we know that already. Now let's see if we can figure out how to graph the line as a vector. So instead of graphing it just as a line, we're going to replace that with a vector. Notice that it's right on top of where the line is. But I could make the vector twice as long, or I could make the vector go in the other direction. Or I could make that go twice as long. Or I could make it go, for example, 1.5 times as long. I have a lot of different choices for how long I make it. Or I could make it an infinite length in both directions, like this. So there's a lot of different things that I can do. I can just take vectors and I can extend it infinitely in both directions, either direction, depending on how long I make this vector. So I just took the vector 3, 1, then I kept sticking it there, or -3, -1. But basically what I'm doing is I'm starting at a particular point. So if I start at 2, 1, for example, then I can add 3, 1, or I can add 6, 2, or I can add -3, 1 or -6, 2. I can basically add anything that goes in this direction. So if I put a scalar multiplier in front, which is going to be our variable, so t is our scalar variable in this case, I can multiply this 3, 1, which, if we notice that this is y and this is x, that makes sense with the slope that we had. So I'm essentially taking a point and a slope, and I'm putting the slope with the variable, which makes some sense. So this is the vector equation of a line as long as I make it an equation. So I would say the vector r, for example, is equal to 2, 1 plus t times 3, 1. You can change 3, 1 however you want as long as it goes along the slope 1/3. And t can be positive or negative. It's any real value. So I could, again, have made this -3, -1. And it ends up being the same thing because t can be any value. So in order to write the vector equation of the line, what we did was we took a position vector, which gives us our initial point. So that was 2, 1. Then we took a direction vector, which puts us in some direction. And then we multiply that by this scalar. So the initial point plus some vector that moves us, and then that gets us anywhere we need to get. This works because the scalar variable can be any real value, positive or negative, so this vector can go forever in either direction, depending on what you make t. So here are some examples. Consider the line in the xy plane through the point -2, 1 with slope 2. First, sketch the line, which we already did. Find its equation in point-slope form. So that would be y minus 1 equals 2 times x plus 2. Now let's do a vector equation for the line. So the first vector would be this one that gets us onto the line. So that position vector would be negative 2, 1. And then after we get there, then we just take vectors that can add or subtract in any direction the correct slope, basically. So we want to add t, which is some scalar multiple, times the slope vector, essentially, some kind of direction vector. So that would be the direction 1, 2, or negative 1, negative 2. So that gives me the vector equation of the line. Now let's find the points on the line that correspond to when t equals negative 1, t equals 0, t equals 2. You just plug in t equals negative 1, you get 2 minus 1, and 2 or 1 minus 2. So notice what that would be, is that would be a vector taking you this way. So that would put you at negative 3, negative 1. T equals 0, it takes you nowhere. So that would put you at negative 2, 1. And if t equals 2, that's going to be a director, or not a director, a direction vector twice as long as 1, 2. So that would be a vector of length 2, 4. That gets you to 0, 5. Problem 2 has this slope-intercept form, so we can look at 3x minus 7 and realize that we have a point and a slope. So the point I would write for the vector form in vector format to give me a location. Then the direction vector is going to be equivalent to having a slope of 3. So that would be 1, comma 3, or negative 1, negative 3, or 2, 6, or anything along those lines. So the vector equation of the line would be 0, negative 7 plus t 1, 3. And there are a variety of ways you can do this again. So you can start at a different point if you want. And you can do anything that would have a slope of 3. So there's a lot of different ways you can do it. Problem 3, find the vector equation of the line through these 2 points. So what we would have to do is, since we have 3 dimensions, we're going to write an r, and that's equal to one of these points plus t times, well, however far it takes us to get in that direction. So we would just do like a 3-dimensional version of a slope here. How far does the x have to move? How far does the y have to move? And how far does the z have to move? So again, t can be any positive or negative number. I could have picked 6, 7, 22 to be my initial point. I could do any sort of multiples of 3, 0, and 41. So I could have chose 6, 0, 82 if I wanted, because then t would just go at a different rate. Number 4, I have 3 lines. What's the relationship between lines A and B? So what we may notice is that they both have the same starting value. So what we would notice is that they intersect at the point 1, 0, 3. Now the relationship between lines A and C, what we may notice is that they clearly don't have the same starting point. But if we look at their direction vectors, they are not the same, but they go in the same direction. So all of the x, y, and z just got multiplied by 2. So what that means is that the quote-unquote slopes are the same. So they're parallel. The reason we know they're parallel is the x values have different y values, and so we know that they're never going to touch. Number 5, write a vector equation of the line through these 2 points. So again, just like we did on number 3 up here, we're going to find a direction vector by subtracting the x's, y's, and z's, then pick one of the points to be a starting point, plus t, your scalar multiple variable, times one of these direction vectors. Lastly, equations of lines of intersecting planes. To find the equation of the line of 2 intersecting planes, you need to know 3 things. You need to know a point on the line of intersection. You need to know a normal vector to one of the planes and a normal vector to the other plane. So these are things that we need to know. So if we look at this picture, we found this point, and then we need normal vectors to both planes. Now the good news is when we have planes that are given to us, like for example, we know that in order to write the equation of a plane, we have a normal vector times or dot x minus x0, y minus y0, z minus z0, and that's equal to 0. So when we did this, we ended up with a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. When you simplify it, you always end up with ax plus by plus cz equals some number. And so what that means is we can very quickly and easily find the normal vector to a plane by just looking at the coefficients of a, b, and c. So because of that, when we're given planes, it's very easy to find these 2 things. Finding the point on the line may not be as easy, but what we know is the cross product of these 2 normal vectors, so the cross product of the blue and the purple, will end up with a vector that's orthogonal to both. And we know that if it's orthogonal to both, that means it's on both planes, since any vector that is orthogonal to n1 is going to be on plane 1, and anything orthogonal to plane 2, or anything orthogonal to n2 is going to be on plane 2. So if it's orthogonal to both or normal to both, it's going to be on both planes. And so what we can do, if it's normal to n1 and normal to n2, it's on plane 1 and plane 2 respectively. So that vector will be a vector that is on this line, and therefore if we use this point and this vector, that gives us the line that intersects, or is the representation of the intersection of both planes. So here's a 3-step process for finding it. Find a point on the intersecting line. We set one of the variables equal to 0 in both equations and solve the resulting system. This works in pretty much all cases. There's a separate video that talks about the cases where it doesn't work, and that's worth looking at for sure. But in the interest of time, so that this video isn't super long, I don't go over those problems here. Number 2, since the line that we got in step 1 lies in both planes, it's perpendicular to both normal vectors. So find the cross product of the normal vectors for each plane, and then you write the equation. So find the line of intersecting planes. So let's just pick a variable to make equal to 0. So I'm going to make z equals 0. That's going to give me the point that's on the intersection of these lines where z equals 0. There's probably points all over the place where z equals 1 or 2 or 3, but we're going to pick 0 just because it's usually easier to pick something where one of them is 0. So if I plug in z equals 0, I get x plus y equals 1 and x plus 2y equals 1. So then I can just change one of the equations so that I can easily add these equations. These go away. This becomes y. This becomes 0. So we know that when z equals 0, y is also equal to 0. And if I plug that in, I get x equals 1. So there is a point that is on both planes on the intersection, and that point that we know is 1, 0, 0. Now the next thing that we have to do is we have to find the cross product of the two normal vectors to the planes. And remember, the normal vectors to the planes are just the coefficients of the x, y, and z. So I'm going to do the cross product ijk. For this one, the normal vector is 1, 1, 1. And for this one, the normal vector is 1, 2, 2. So now what I'm going to do is I'm going to find a normal vector to both of these. So if I if I do the thing with I end up getting 0. If I do the thing with j, I end up getting 2 minus 1. But remember, that's a negative 1. If I do it with k, I get 2 minus 1. So I have 0, negative 1, 1. That is my direction vector. So I have a point and a direction vector. So I have r equals 1, 0, 0 plus t 0, negative 1, 1. Number 7, now we're going to find the line of intersection here. Let's make x equal to 0. Again, you can pick whatever variable you want. So we have 2y plus z equals 1 and negative 2y plus z equals 2. Now notice I'm being pretty intentional about the things that I picked. Like, for example, x equals 0 makes sense because the y's are going to cancel off pretty quickly. So when I add these two things together, I get 2z equals 3. So z equals 3 halves. And then I can plug that back in. So I get 2y plus 3 halves equals 1. I just plugged it into the top equation. 2y equals negative a half. Y equals negative a fourth. So a point on the intersection line is 0, negative a fourth, 3 halves. Again, there are plenty of points you can pick. You could apply it plugged in x equals 1, x equals 20 for all I care. It doesn't really matter. Now we need to find a normal vector to the two normal vectors to the plane. So I'm going to put 3, 2, 1, 1, negative 2, 1. And then if I do my cross product situation, I end up with 2 minus negative 2. I end up with 3 minus 1, but remember this one has the opposite sign. And for k, I end up with negative 6 minus 2. So my final answer would be my equation of the line is 0, negative a fourth, 3 halves is just any point that's on the line, or the intersection line. That's the one that I ended up with, times t, 4, negative 2, negative 8. Also notice that 4, negative 2, negative 8, all of those are multiples of 2, so it's actually pretty easy to get a different answer by dividing all of these by 2 if you wanted. One more thing to talk about is, this is something that may motivate you to watch the other video. What would have happened if, instead of on number 6, if I didn't plug in z equals 0, if I plugged in x equals 0? So if I plugged in x equals 0 and I tried to do that just like I did in number 7, I'd end up with y plus z equals 1 and 2y plus 2z equals 1. If I solve this system, I end up with negative 2y minus 2z equals negative 2, and 2y plus 2z equals 1. I'd end up with 0 equals negative 1, and that would kind of freak me out. So if I end up with a situation like that, That's something that you may want to watch the other video just to figure out how we would handle that. So notice that when I plugged in z equals 0, I got an answer. When I plugged in x equals 0, I get something that's confusing. So that is something that indicates that this plugging in 0 for one of the points doesn't work all the time, and there may be cases where you have to try something else.